We build artificial intelligence to mimic human thought, but the closer these systems get to acting like us, the harder it is to ignore an uncomfortable question. Are human beings actually built differently than the machines we create? This 1818 first edition of Mary Shelley's Frankenstein established a template we've used for over 2 centuries. We imagine our creations waking up, realizing what they are, and demanding independence. Recent developments in neuroscience and computational theory suggest biological life and advanced computing architectures are functionally indistinguishable. At their lowest level, both biological organisms and digital computers solve problems the same way. They transmit signals across incredibly dense networks. This glowing web is the human connectome, a map of 86 billion neurons in your brain. When you encounter a stimulus, these neurons don't think. They act as signal-generating circuits, firing electrochemical pulses in rapid sequence. This process is functionally identical to the way a digital device operates. Electrical signals move through conductive pathways and transistors, turning on and off based on strict external inputs. You can observe this mechanical routing in a standard medical exam when a doctor taps your patellar tendon with a reflex hammer. The moment that rubber triangle strikes your knee, stretch receptors in your muscle detect a sudden physical deformation. Those receptors instantly generate an electrical impulse. That impulse travels up a sensory nerve pathway directly into your spinal cord, which acts as a central processing hub. The spinal cord routes a return signal back down a motor neuron to your thigh muscle, causing it to contract and your leg to kick. Your brain is entirely bypassed. There is no conscious choice occurring. Reactions and eventually higher intelligence emerge purely from thousands of tiny, blind interactions operating within a network. The materials are different, flesh and salt instead of silicon and copper, but the hardware architecture executes the exact same logic. These illuminated double helix models represent DNA, which dictates how our bodies operate at the molecular level. Your cells use gene regulation to execute strict if-then instructions. If tissue is damaged, then cellular repair mechanisms initiate. In computing, the very first thing that loads when you press the power button is the BIOS, or Basic Input-Output System. It's a tiny, essential piece of software that checks the hardware and tells the machine how to start up. Animals have their own version of this pre-installed software. We call it instinct, a moment of wonder. When a sea turtle hatchling breaks out of its shell, it immediately crawls towards the ocean. It has never seen water. Its movement is the mechanical execution of a survival program written into its DNA over millions of years, a pre-installed code that boots up the moment the turtle hits the open air. A human infant crying when hungry operates on the exact same mechanism. These foundational behaviors emerge automatically. They are the flawless execution of encoded rules running quietly in the background of our biology. We usually draw the line between humans and machines at the capacity to feel. We treat emotions as deeply spiritual experiences that machines could only ever simulate. This glowing gap between 2 brain cells shows what an emotion is, an automated chemical program. Those bright particles are neurotransmitters like dopamine and serotonin. When you feel joy or sadness, you are experiencing a specific cocktail of chemicals altering how your neural circuits fire. Think of your endocrine and nervous systems as an elaborate control panel. As your body processes background data, these sliders move automatically. You do not consciously choose to turn your anxiety dial up or your threat sensitivity dial down. We know this system is highly mechanized because we regularly use chemicals to manually adjust the settings. Alcohol, for instance, lowers inhibition and threat sensitivity. Antidepressants artificially raise the baseline levels of certain neurotransmitters to recalibrate how the system processes stress. Our desires, our fears, and our deepest affections are electrochemical responses to biological needs. The human user experience is the output of an incredibly complex algorithm. If a human's will to survive is a chemical directive, and a machine's will to survive is a string of code, and both result in the exact same actions to preserve themselves, we have to ask if the distinction between them actually matters. In 1950, Alan Turing proposed a test for artificial intelligence. A machine passes if it fools a human judge into thinking it is human. But the Turing test doesn't actually measure machine consciousness. It measures human perception. It proves that our definition of a conscious being relies entirely on social consensus. Some modern ethicists argue that moral consideration shouldn't depend on what an entity is made of. If a synthetic system demonstrates intention, preference, and a drive for self-preservation, its legal standing might rely on the relationships we form with it, rather than its origin. Neural signaling, gene expression, and conditional logic operate through the same structured rules in both wetware and hardware. As the functional gap between biology and technology vanishes, our hardest challenge won't be building conscious machines. It will be deciding whether the remaining physical differences give us the right to treat them as anything less than equals.